Assalamualaikum and hi everyone. Welcome back to LU6 Molecules and Molecular Structures. For today's lecture, we're going to continue for 6.4 Molecular Shapes. By the end of this lecture, you should be able to identify polar and nonpolar molecules and explain hybridization of orbitals. From previous lesson, you have learned on how to determine the molecular shape of a molecule. So for today's lesson, you're going to learn on how to determine the polarity of the molecule. So what is so important about polarity? Polarity is important because it can determine the solubility of a molecule. Molecule with high polarity or polar can mix well with other polar compounds such as water, while molecules that are nonpolar or have a very low polarity can mix well with other nonpolar compounds such as oil. Polarity also affects the strength of intermolecular forces. Nonpolar molecule only exhibits the van der Waals force, while polar molecule exhibit the dipole-dipole interactions. Dipole-dipole interaction is stronger than the van der Waals forces. As a result, the boiling point and melting point of polar molecule is stronger than nonpolar molecules. Determination of polar or nonpolar molecule depend on the distribution of electrons. A polar molecule is one in which one side of the molecule has a slight positive charge and the other side has a slight negative charge. A nonpolar molecule tends to have a symmetrical distribution of charge, while a polar molecule tends to have uneven or unsymmetrical distribution of charge. A polar bond formed from unequally shared electrons. It consists of two poles, which is partially positive and partially negative. The greater the difference in electronegativity, the more polar of the bond. The electronegativity can be represented by the Pauling scale. For example, you have HCl here. Between H and Cl, by using the trend of the periodic table, you know that Cl is more electronegative than H. So that means Cl will have more electron attracted towards the atom rather than the hydrogen. This will resulting in the Cl will become a partially negative while H will become the partially positive. These are the Pauling scale for each of the atoms in the periodic table. The Pauling scales also represent the trend for the electronegativity in the periodic table, where when you're going across the period, the electronegativity will increase, while when you're going down the group, the electronegativity will decrease. To determine whether the molecule is a polar or nonpolar, you need to find the molecular dipole moment of the molecule. Molecular dipole moment is a measure for the polarity of a covalent bond. The vector sum of the individual bond dipole moment in a molecule measured in unit d by d. So these are the example for the bond dipole or d by for each of the bond in the other compound. Some molecules that contain polar bonds have no overall polarity. This occurs when the dipole moment from each of the bonds cancel in the molecules as a whole. This happens in molecules that are symmetry, such as with linear shape and tetrahedral shape. Please remember that nonpolar molecules tend to have a symmetrical shape. To determine the polarity of a molecule, we need to identify, number one, whether the molecule has dipole moments or not, and number two, the arrangement of this bond in space. When the centers of negative and positive charge are separated, we say that the molecule has a dipole moment. So that is why it is important to determine the dipole moment of a molecule so that we can know the polarity of the molecule. For example here, you have HCl. You know that between H and Cl, Cl is more electronegative than H. So Cl will attract more electron rather than H, and Cl will become the partially negative, while H will become the partially positive. The movement of dipole moment will come from the positive to the negative. So if there is a dipole moment movement, the molecules will be polar molecules. Molecule geometry is also a critical factor in determining if a molecule has a dipole moment or not. For example, NH3. The polar bond between H and N, you know that N is more electronegative than H. So H will be the partially positive and N will be the partially negative. And the movement for each of the polar bond between H and N will come from the positive to the negative. It will come from the H to the N, and to determine whether the molecules are polar or nonpolar and what is the effect of molecular geometry. So as you can see here, the whole polarity will come upward. This is because the the three dipole moment for each of the H and polar bond will meet at the center, and it will force the polarity and will force the dipole moment to move upward. There are molecules that have polar bonds, but each has a zero dipole moment. As a result, the molecules will become a non-polar molecules. For example, carbon dioxide. These are the Lewis structure for carbon dioxide, and the molecular shape of carbon dioxide is linear. Carbon will become the central atom, and oxygen will become the side atom. Between carbon and oxygen, it is known that oxygen is more electronegative than carbon. So that means oxygen is a partially negative, while carbon is a partially positive. For each of the bond between carbon and oxygen, the movement of dipole moment comes from the carbon towards the oxygen because it comes from a partially positive to the partially negative, while the other side of the carbon and oxygen bond, the movement of the dipole moment also comes from the carbon towards the oxygen. This is because the oxygen is a partially negative while the carbon is a partially positive. So as you can see here, even though the even though the bond is a polar bond, the molecular shape will comes into effect on why it can determine whether the molecules are polar or not. So the molecular shape for carbon dioxide is a linear. So when both of the dipole moment goes to the right and goes to the left, this will cancel out each of the dipole moment because both of the side atoms are the same. Both of the side atoms are oxygen. Both have the same electronegativity, and therefore it will cancel out the dipole moment. So the dipole moment will equal to zero. So when the dipole moment is equal to zero, the molecules will become a non-polar molecules. The same cases happen for the next example, which is a boron trifluoride. Between boron and fluorine, we know that fluorine is more electronegative than boron. So the movement for each of the for each of the bond will come from the boron towards the fluorine. So when you have determined whether the bond is polar or not, use the molecular shape to determine whether the molecules are polar or nonpolar. So as you know, for trigonal planar, the bond angle for each of the bond is 120 degrees. So this will make the dipole moment will cancel out each other. So the dipole moment will equal to 0. The same cases also occurs on the carbon tetrachloride. Carbon tetrachloride has a molecular shape of tetrahedral. Between chlorine and carbon, chlorine is more electronegative than carbon. So the movement of the dipole moment will come from the carbon towards the chlorine. But for the molecular shape of tetrahedral, each of the bond angle is 109.5 degree. So that is why the dipole moment between each of the chlorine atom and the carbon atom will cancel out each other. So when it cancel out each other, the dipole moment will equal to 0. And when the dipole moment is equal to 0, the molecules will become a non-polar molecules. A molecule is considered polar if the molecule possesses a resultant dipole moment. So what does it mean by a resultant dipole moment? For example, you have formaldehyde. So for a formaldehyde, the carbon will become a central atom and the oxygen and two hydrogen will become the side atom. So for both of the carbon and hydrogen atom, the bond is a polar bond. This is because hydrogen is less electronegative than carbon. So carbon will become the partially negative while hydrogen will become the partially positive. So for both of the carbon and hydrogen atom, the bond is polar and the movement of the dipole moment for carbon and hydrogen come from hydrogen towards the carbon. But for the carbon and oxygen, oxygen is more electronegative than carbon. So carbon will become the electropositive while oxygen will become the electronegative. So the movement of the dipole moment will come from the carbon towards the oxygen from positive to negative. So as you can see here, there for the total dipole moment, there is no cancelling each other. The hydrogen will come from carbon and the carbon will come to the oxygen. So the direction of the dipole moment will come from the left to the right. So this will resulting in the dipole moment of a molecule. So when a molecule has a dipole moment, it will become a polar molecule. Next, for water, the oxygen will become the central atom and the hydrogen will become the side atom. So for each of the bond between hydrogen and oxygen, the bond is a polar bond. This is because oxygen is more electronegative than the hydrogen. So the movement of the dipole moment will come from the hydrogen towards the oxygen. So as you can see here, even though both of the side atom is the same, which is hydrogen, this is why the molecular shape is important to determine whether the molecule is a polar or not. So for water, the molecular shape is V-shaped. So if the shape cannot cancel out each other and the dipole moment cannot cancel out each other because the shape is not symmetrical, so the direction of the dipole moment will come from the left to the right. So when a molecule possesses a dipole moment, it will also become a polar molecule. The same cases occur on ammonia. Even though all of the side atom is the same, which is hydrogen, for ammonia, both of each of the bond between hydrogen and nitrogen is a polar bond. Because hydrogen is less electronegative than nitrogen, so the dipole moment will come from hydrogen towards the nitrogen. So even though the side atom is the same, but because of the shape is not symmetrical, the direction of the dipole moment will come from downward towards upward. So when a molecule possesses a dipole moment, it will resulting in the molecules is a polar molecules. Cis-trans isomers often differ in the magnitude of their dipole moments and a polar compound. Cis-trans isomers have the same molecular formula and the same side atom, but the only thing different between cis and trans isomer is the placement of the side atom. For example, here we have cis-dichloroethene and trans-dichloroethene. As you can see, for cis-dichloroethene, we have 2 Cl and 2 hydrogen. And for trans-dichloroethene, we have 2 Cl and 2 hydrogen atom as the side atom too. The only thing that different between cis and trans are the placement for their side atom, where for the cis isomer, the side atom are placed at the same place as the other atom, where the two same atoms are placed at the same place, at the bottom and at the top. While for trans, the side atom will be placed opposite from each other. You will learn more about the cis and trans isomer in LU7. So as you can see here, for the cis isomer, it is a polar molecule because it has a dipole moment. While for the trans molecule, it will become a nonpolar molecule because it has a zero dipole moment. This is because the dipole moment cancel out each other. So the first dipole moment will go upward while the second dipole moment will go downward. This will cancel out each other. So this dipole moment will cancel out each other, resulting in the dipole moment is equal to 0. Exercise 1. Choose the molecules that has polar bond but considered as nonpolar molecules. So we have 4 molecules which are ozone, borane, hydrogen cyanide, and sulfur trioxide. So to determine whether the molecules are polar or nonpolar, you need to find the dipole moment first. But for this question, it only asks for the nonpolar molecules, but it also contains a polar bond. So for the first one, for the first molecule, which is ozone, you know that the Lewis structure for ozone is like this. But as you can see here, for ozone, it doesn't have a polar bond because all of the atoms are the same. The central atom and the side atom are the same. So ozone is not the answer. But next you have borane, BH3. So for borane, you have the Lewis structure look like this, which is a trigonal planar. So first thing first, determine whether the bond is a polar bond or not a polar bond. So for borane, it is a polar bond because the central atom and the side atom is different and the electrons are shared unequally, where this is because hydrogen is a partially positive and boron is a partially negative. This is because boron is more electronegative than hydrogen. So the dipole moment will come from hydrogen towards the boron. So do the same thing for other bond between the hydrogen and boron. So as you can see here, the dipole moment comes from hydrogen towards the boron and it meets at the center. And since the side atom is the same, so it will resulting in the dipole moment is equal to 0 because it cancel out each other. So when it cancel out each other, the dipole moment equal to 0. The molecules will become a nonpolar molecules. Next, we have hydrogen cyanide. So for the Lewis structure of hydrogen cyanide, you have the carbon as the center And nitrogen and hydrogen is the side atom, but you have a triple bond at the nitrogen and a single bond at the hydrogen. So as you can see here, for hydrogen cyanide, it is a polar bond because it has different central atom and different side atom. But in terms of polarity, for the hydrogen and carbon, the dipole moment will come from the left to the right because carbon is more electronegative, so it is a partially negative, and hydrogen is a partially positive. While for carbon and nitrogen, the dipole moment for carbon and nitrogen is also come from the carbon towards the nitrogen. This is because nitrogen is more electronegative, so nitrogen will become the partially negative and carbon will become the partially positive. So the dipole moment will come from carbon towards the nitrogen. So the total dipole moment, the direction of dipole moment will come from the left to the right. So hydrogen cyanide is a polar molecule. So it's not the answer. And lastly, sulfur trioxide. For sulfur trioxide, the Lewis structure will look like this. So first thing first, determine whether the bond is a polar bond. So it is a polar bond because the central atom and the side atom is different. After you have determined whether it's a polar bond or not, check for the dipole moment for each of the bond between S and O. So S is less electronegative than O. So O will become the electronegative while S will become the electropositive. So the dipole moment will come from S to O. The other dipole moment for S to O, and this one also come from S to O. This is because S is less electronegative than O. So when you have the dipole moment, check for the direction of the dipole moment. So for these cases, sulfur trioxide has a molecular shape of trigonal planar, and the bond angle between each of the bond is 120 degree. So that means it will cancel out each other. This is because the side atom is the same. Side atom is all oxygen. So the force of the attraction of the electron is the same. So that's why the dipole moment will cancel out each other. So when the dipole moment cancel out each other, the dipole moment will equal to 0 and the molecule is a non-polar molecules. Exercise 2. Identify whether the following liquids are polar or non-polar. For number 1, liquid nitrogen, the Lewis structure for liquid nitrogen will have a triple bond between each of the nitrogen. So to determine whether the molecules are polar or non-polar, we need to check whether the bond is a polar bond or not a polar bond. So between the liquid nitrogen, it doesn't have any polar bond. This is because both of the side atom and the central atom are the same. So if it doesn't have any polar bond, so that means it doesn't have any dipole moment. So when there is no dipole moment will equal to 0. So when dipole moment equal to 0, that means for liquid nitrogen it is a non-polar. Next, you have the hydrogen fluoride, HF. So for hydrogen fluoride, the Lewis structure will have a single bond between the hydrogen and fluorine. So first thing first, check whether it is a polar bond or not. So for hydrogen fluoride, it contains a polar bond because fluorine is more electronegative than hydrogen. So fluorine will become the partially negative while the hydrogen will become a partially positive. So the movement of the dipole moment will come from the hydrogen, come from the partially positive toward the partially negative. And the direction of the dipole moment will come from the left to the right. So that means the dipole moment will have a value. So dipole moment is not equal to 0. So when dipole moment is not equal to 0, that means the molecules are a polar molecules. Next, you will have a benzene. So for benzene, the Lewis structure for benzene will look like a ring. So this is a Lewis structure for benzene where each of the carbon will have a H atom attached to it. So first thing first, check either the benzene has a polar bond or not. So for benzene, it has a polar bond between the carbon and hydrogen. And the dipole moment will come from the hydrogen towards the carbon. This is because carbon is more electronegative than hydrogen, so carbon will become the partial negative while the hydrogen will become the partially positive. So for all of the hydrogen and carbon bond, the dipole moment will come from the hydrogen towards the carbon. And lastly, all of these dipole moment will meet in the center. So the direction of the dipole moment will meet in the center. So the direction of the dipole moment will become 0. This is because the dipole moment cancel each other. So when the dipole moment equal to 0, that means the molecule is a non-polar molecule. And lastly, for methanol, the Lewis structure for methanol will looking like this. You have one oxygen and three hydrogen attached toward the central atom, which is right now your central atom is carbon. So check whether it has a polar bond or not. So for methanol, it has a polar bond. You have a polar bond between carbon and hydrogen, and you have a polar bond between carbon and oxygen. So for the polar bond between carbon and hydrogen, the, the dipole moment will come from hydrogen towards the carbon because carbon is more electronegative than hydrogen. But for carbon and oxygen, the dipole moment will come from carbon towards the oxygen. This is because oxygen is more electronegative than carbon. And lastly, check for the direction of the dipole moment. The direction of the dipole moment will come from the left to the right. This is because there is no cancelling out each other, so they cannot cancel each other. So when there are a dipole moment, so the dipole moment is not equal to 0. So when the dipole moment is not equal to 0, that means it is a polar molecule. So let's check your answer. So for A, it is a nonpolar. For B, it is a polar. C, it is a nonpolar. And D is a polar. You have learned on how to determine the polarity of a molecule. So let's move on to the hybridization of a covalent bond. For covalent bond, a bond is formed when two or more atoms share their electron to achieve a stability in octet or duplet configuration. So these bonds are assumed to be formed by overlap of atomic orbitals, which is s or p or d orbitals. The strength of covalent bond is proportional to the area where the atomic orbitals overlap. The sigma bond is formed by the head-on overlapping, while the pi bond is formed from sideways overlapping. Please take note that the sigma bond is a single bond, while the pi bond is the double bond. So what does it mean by the head-on overlapping of orbital to form a bond? For example here, the formation of covalent bond between two hydrogen atoms. You know that the hydrogen atom has a configuration of 1s1. So it needs one more electron to become a duplet configuration to become a 1s2 configuration. So it will form a covalent bond with other hydrogen so that both of the hydrogen can achieve a duplet configuration. So the single bond, also known as the sigma bond, is formed by the head-on overlapping between the two 1s orbital from each hydrogen atom. So the 1s1 orbital from the hydrogen 1 and the 1s1 from the orbital hydrogen H2 will form a bond by overlapping the orbital. The other example for the head-on overlapping of orbital to form a bond, formation of covalent bond between hydrogen atom and fluorine atom. So the sigma bond is formed by the head-on overlapping between the 1s orbital from hydrogen atom and 2p orbital from the fluorine atom. So you have a hydrogen atom which is a 1s1 configuration and the fluorine atom which will have a 1s1, 2s2 and 2p5 configuration. So the hydrogen atom need one more electron to form a duplet configuration, while the fluorine atom will need one more electron to form an octet configuration. So the head-on overlapping between the hydrogen and fluorine atom will occur between the 1s1 of hydrogen and the 2p5 of the fluorine, or the 2p orbital. So this 1s1 and the 2p5 will overlap to form a bond between the hydrogen and fluorine. Another example of the head-on overlapping of s and p orbital is the formation of covalent bond between two fluorine atoms. So you know that fluorine atom has the configuration of 2s2 and 2p5. So both of the fluorine atom need one more electron so that it can achieve an octet configuration. So these both fluorine atom will form a bond between each of them so that both can achieve an octet configuration. So the fluorine number 1 and fluorine number 2 will form a bond by overlap both of its p orbital to form a bond. Sigma bond for the formation of covalent bond between the fluorine atom is formed by the head-on overlapping between two 2p orbital from each fluorine atom. For the sideways overlapping, it involves in the overlapping of a pi bond. So a pi bond comes from a double bond. For example, the formation of double bond between two carbon atoms. So two carbon atoms will form a double bond between each other, and it will have a one lone pair each, so it can become an octet. So one of the bond between the carbon atom is a sigma bond, while the other one bond is a pi bond. Pi bond is formed by sideways overlapping between two p orbitals from each carbon atom. I will show you how the pi bond overlap in the carbon atom between the two carbon atom after you have learned what is hybridization. So what is hybridization? Hybridization is the process of mixing together two or more atomic orbitals that have the similar energies. The new atomic orbitals produced are called hybrid orbitals. Please take note that we mainly focus on the hybridization of central atoms only. So these are the examples on the hybridization between the 2s orbital and the 2p orbital. As you can see here, the 2s orbital will mix with the 2p orbital to form a sp3 hybridized orbital. So what does it mean by sp3 hybridized orbital? The sp3 hybridized orbital will use all of the s orbital and all of the 3 orbital. So that's why it is s and p3. So all of the s orbital is used and all of the 3 p orbital is used. So you will get a sp3 hybridized orbitals. These are the examples on the type of hybridization that can exist. So for the type of hybridization sp, the hybrid orbitals will come from the 1s and 1p orbital only. The shape of the molecule for this type of hybridization is linear. Next, for the sp2, according to the name, that means it only have one s orbital and two p orbital is used to form the hybrid orbital. Next, for the sp3, one s orbital is used and all of the p orbital will be used to form the hybrid orbital. Next, you have the sp3d1, which means one s orbital is used, 3p orbital is used, and also one of the d orbital will be used to form a hybrid orbital, and so on. An example on how the hybridization works. Example 1, carbon in methane. In isolated C atom, which is the central atom, the 2s and all 2p orbitals are mixed to form sp3 hybrid orbitals. In methane, the sp3 hybrid orbitals overlap with the half-filled 1s orbital of 4 hydrogen atoms and form 4 CH bonds which point towards the vertex of a tetrahedral. So for example, you have a methane which is CH4. So the electron configuration for carbon is 2s2 and 2p2. So draw the orbital first, 2s and 2p. So for the 2s, it will be full of electron, and 2p, we will have 2 electron only based on the configuration. Next, from the molecular formula, or if you draw the Lewis structure, which is CH, CH, carbon will form 4 bonds with hydrogen. But in a unhybridized state, for this current unhybridized state, there are only 2 empty places that can form a covalent bond. Remember that covalent bond is a bond that formed when the electron share when the atom share the electron. So right now, carbon only has two p orbital that have one electron only. So to form a bond, for example, hydrogen with a 1s orbital can only come here to form a bond with the carbon. So right now, in the current state, in the current unhybridized state, carbon can only form 2 bonds with H. So it becomes CH2, but we need it to form a CH4. So how does the carbon can form 4 bonds with hydrogen? So that is why we do the hybridization. So you need to hybrid the 2s and 2p orbital to form an orbital, to form a hybrid orbital. So you mix first. So you mix the two orbital, it will become like this. Okay. So the electron from the 2s will excited and go to the p orbital. So this is possible because right now the energy level between the 2s and 2p is similar because it is hybridized. Okay, so the electron can move to the other place so that it can become a single electron. So it will become like this. So right now, in this hybridized state, carbon can accept 4 electrons to form a bond. So that means hydrogen, which has 1s1, can form a bond with carbon if it donates its electron, if it shares its electron with the carbon, and another hydrogen, which also has 1s1, can form a bond with carbon if it shares its electron with carbon. Another hydrogen also come, 1s1, so it can form a bond with the carbon. And lastly, another hydrogen can come to form its bond with the carbon. Okay, so right now it is possible for carbon to form 4 bonds with hydrogen. This is because carbon has 4 empty places, or 4 places for the hydrogen to come and share the electron. Another example on hybridization is the hybridization for nitrogen in ammonia. One of the sp3 orbitals is filled with a lone pair electrons. As you can see from the Lewis structure of ammonia, the nitrogen is the central atom. It will bonded with 3 hydrogen atoms and it will have a lone pair. So for the electron configuration of nitrogen, since nitrogen is the central atom, we will focus on the nitrogen for the hybridization of the ammonia. So the electron configuration for nitrogen is 2s2 and 2p3. In an unhybridized state, the configuration is 2s2 and 2p3. For this unhybridized state of nitrogen, the hybridized state of nitrogen will be the same with its unhybridized state. There is no need for the movement for the electron from 2s because, as you can see here, the hydrogen can already form a bond with the nitrogen because each of the p orbital is available and sufficient for it to form a bond. So from the Lewis structure, nitrogen need to form 3 bonds with hydrogen. Based from its unhybridized state, it has 3 empty or 3 single electron, and to form a bond it need to form a pair. So this hydrogen will form a bond with the first orbital to become a bond, and then another hydrogen can form a bond with the ammonia with the nitrogen, and another hydrogen can form a bond with the nitrogen because it still has a available single electron. So that means the hybridized state of nitrogen is the same with its unhybridized state. But the difference between the hybridized state of nitrogen atom and the carbon atom from the previous example is, as you can see here, it has a lone pair. So this lone pair shows that the ammonia, the nitrogen has a lone pair for its atom. So, and for the state of the hybridization, since you use all of the s orbital and all of the p orbital, so the type of hybridization is sp3. Example 3, boron in Bf3. Central boron atom is sp2 hybridized. Each sp2 orbitals overlap with the 2p orbital of an F atom, forming 3 bonding pair. So let's check whether the hybridized state is correct or not. So first thing first, draw the Lewis structure Bf3. So Bf3, it will form 3 bond with F, supposed to form a 3 bond with F, doesn't have any lone pair because boron can exist in incomplete octet. And we mainly focus on boron because boron is the central atom, and the configuration for boron is 2s2 2p1. So draw the unhybridized state first, which is 2s and 2p. So in the unhybridized state, in this unhybridized state, boron can only form one bond to other atom. This is because it only has one single electron. So to form a bond, it needs to share this electron with other atom so that it can form a pair and then it can form a bond. But since boron only have one available single electron, that means it need to hybridize because it need to form 3 bond with the fluorine. But right now in its unhybridized state, it can only form one bond only. So for the hybridized state, you combine all of the 2s and the 2p orbital first. So this is s and this is p. So when the energy level is the same, you can move the electron from the s orbital to the p orbital, and then it will become like this. So this is one single electron, another single electron, and this is another single electron that you move from the previous s orbital. Okay, so this is the p orbital and this is the s orbital. So right now, if you try to form a bond with F, it can form 3 bonds with F right now because it has 3 available single electron. So the F can form a bond when it share electron at the p orbital, and then another F can form a bond when it share its electron at the p orbital too, and another fluorine can form a bond with boron when it share its electron at the s orbital. So right now, boron can form 3 bonds with fluorine, and for the hybridized state, as you can see here, you use all of the s orbital, and you only use 2 of the p orbital. So that means the type of hybridization is sp2 because you only use 2 of the p orbital available. And the last example is carbon in ethene. For the hybridization of carbon in ethene, it will involve the formation of a second bond, also known as the double bond. For a formation of double bond, you will have 2 types of bond. The first one is a sigma bond, and the second bond is called as the pi bond. For the hybridization of carbon in ethene, so the Lewis structure for ethene will be look like this, where you can focus on one of the side only. So focus on this side only because it has the same side atom and it has the same number of bond. So for this carbon, it need to form a single bond with two hydrogen, and it need to form a one single bond with another carbon and a pi bond with a carbon 2. So for the hybridization, we focus on the central atom only. So carbon will have the electron configuration of 2s2 and 2p2. So you draw the unhybridized state first, 2p. So the 2s will be full while the 2p only have 2 electrons. So based from the Lewis structure, it has 3 sigma bond. The first sigma bond is for the one hydrogen, another sigma bond is at another hydrogen, and the third sigma bond is for the formation of bond between the carbon and another carbon. But right now, in its unhybridized state, this is the unhybridized state, this carbon can only form two sigma bond with other atom because it only has two single pair of electron. So you need to hybridize the 2s and 2p orbital. So it will become like this, sp. So to make room for a more bond to be formed, so you need to move one of the electron from the s orbital to the p orbital, and then it will become like this. So each of the orbital have one single electron right now. But please take note that the carbon atom only need 3 electrons to form a sigma bond. So this is S and this is P. So it will use the electron from the S and 2 electrons from the P orbital only. For example, it will use the S electron to form a bond with the another carbon to form a bond, and this 2p orbital will be used to form a bond with hydrogen, sigma bond with the hydrogen. So you will have one left of the p orbital, so this left p orbital will become the unhybridized p orbital. This is the unhybridized p orbital. Unhybridized. So this unhybridized p orbital will form the pi bond, which is the overlapping by the sideways. So for the formation of pi bond is actually when you have an unhybridized p orbital or unhybridized d orbital. An exercise for you so that you can master the hybridization. State the type of hybridization of the central atom in the following molecules. Number 1, BH3. So to determine the type of hybridization, you can draw the Lewis structure of the molecule first to determine what is the type of bond that exists in the molecule. So right now, for BH3 molecule, the Lewis structure, it only forms a 3 sigma bond or 3 single bond with hydrogen. So it doesn't have any double bond, so it doesn't need to form a pi bond. So focus on the boron only because we need to focus on the central atom. So the configuration of boron is 2s2 and 2p1. So draw the orbital 2s and 2p. So the 2s will have full configuration and 2p only have one electron. So in its unhybridized state, boron can only form one sigma bond because it only have one available single electron. But based from the Lewis structure, it need to form three sigma bond. So to accumulate the number of sigma bond, you need to hybridize the s and p orbital. So hybridize the s and p orbital first. And when the energy level is the same, you can move the electron from the s orbital to the p orbital. So the hybridized state will become, it will have three available single electron now. Okay, so since you already have all of the three single electrons, so that means right now boron can form three sigma bond. So when it can form three sigma bond, then it means it can form three bond with the hydrogen. So right now it only use two of the p orbital. So the hybridized state for the boron is sp2. Okay, so for BH3, the hybridization state is sp2. So next is the SF6. So for SF6, you can draw the Lewis structure first. So you have 6 fluorine form a bond with the sulfur. So that means sulfur need to form 6 sigma bond for each of the chlorine. So focus on the sulfur only. So for the configuration of sulfur, you will have 3s2, 3p4. So draw the unhybridized state first. So in the unhybridized state, you will have 3s and 3p. You have 4, 1, 2, 3, and 4. So right now, in the unhybridized state of sulfur, as you can see here, it can only form two sigma bond because it only have two available single electron. So it can only form two sigma bond. But based from the Lewis structure, it need to form six sigma bond. So even though you need to mix the s and p orbital, so when you mix the s and p orbital, you still cannot get enough of the electron because it cannot move from the s and p orbital anymore because there are no place for the electron to move. So if you move the electron from the s orbital to this orbital, this one will become full and this one will lose one electron, and still you still get the same cases. So what you can do for sulfur, it will have an empty d orbital. So in sulfur you can have an empty d orbital because the d orbital is not used, so you doesn't need to write the d orbital. Actually you have the d orbital here, but it only have 3d0 because there is no electron in the 3d, so that's why you doesn't need to write the 3d. But actually for sulfur it has an empty d orbital, so that means the electron from the s can move to the d orbital and the electron from the p can move to the d orbital. So when you move the electron right now, it will become, so now it have 6 single electron. So when it has 6 single electron, each of these electron can be shared with the fluorine, and each of these electron can form a bond with the fluorine. So please remember how many s orbital, how many p orbital, and how many d orbital that you use. So right now you use one s orbital, so s, and you use 3 p orbitals, so that means sp3, and you use 2 of the d orbitals, so it is an sp3 d2. So put your answer here, sp3 d2. Okay, so next we will do for the PCl5. So for the PCl5, first thing you can do, you can always draw the Lewis structure first. So as you can see from the Lewis structure, the phosphorus need to form 5 sigma bond with the chlorine. So the electron configuration for phosphorus is 3s2, 3p3. So draw the unhybridized state first. 3s and 3p. Okay, so for this unhybridized state for phosphorus, as you can see here, phosphorus can only form 3 sigma bond because it only has 3 single electron. But right now, based from its Lewis structure, it need to form 5 sigma bond. So what we can do is we can use the empty d orbital. So you need to hybrid 3s, 3p, and 3d orbital. So S 1, 2, 3 for P, and 1, 2, 3, 4, 5. Okay, right now you have hybrid the S, P, and D orbital. So you can move one electron from the S to the D orbital because it already has the same energy level. So it will become, like this. Okay, so SPD. Okay, so right now it has 5 available single electrons. So that means it can form 5 sigma bond with other electron. So now it's possible that phosphorus can form 5 bond with Cl. And remember that how many of each of the orbital you use. So for s orbital, you use all of the s orbital, so s. And for the p orbital, you use all of the p orbital, so that means sp3. And for the d, you only use one d orbital, so sp3d1. So the hybridization for PCl5 is sp3d1. Okay, so let's move on to the last question for today, which is the H2O or water. For H2O, to find the hybridization of H2O, you can draw the Lewis structure first. So O will be the central atom, And at oxygen, it will have two lone pair. So this is the Lewis structure for H2O. So focus on the oxygen. So for the configuration of oxygen, you will have 2s2 and 2p4. So draw the Lewis structure first. Draw the Lewis structure pula. Okay, so draw the orbital for each of the orbitals. So 2s and 2p4. 1, 2, 3, and 4. Okay, so for based from the Lewis structure, oxygen need to form a sigma bond with hydrogen, and it only need to form two sigma bond. And based from its unhybridized state, it already has the sufficient electron that can be form a bond with the hydrogen. So it already has two single electron, but you still need to hybridize the s and p orbital because it is an overlap sigma bond. So sp. So right now, as you can see, for the hybridized state of water, it is an sp3. But as you can see from the hybridized orbital, you have two lone pair. This is because at oxygen, it has two lone pair. Okay, so let's check our answer, whether it is correct or not. So I hope that you try this question. You can pause the video first and then you can check for the answer. I hope that you try for this question. Okay, so for the answer, so for the A, you get sp2, sp3d2, sp3d1, and lastly you will get sp3. So congratulations to those who try and get the correct answer. And that's it for today's lecture. I hope that from today's lecture, you can determine the polarity of a molecule and also the hybridization for the central atom of a molecule. We will meet again for the next lecture, our last lecture for LU6, which is intermolecular forces and hydrogen bonding and physical properties. Thank you so much, and I hope that you have fun for today's lecture. See you again, and thank you.